Okay, so let me say that again because that's probably confusing to some people. So this moment, this moment axis is along a line of symmetry. So you know that this axis is a principal axis for sure. Okay, so the neutral axis and the moment are going to coincide. How about here? This is not along a line of symmetry, so you can't be for sure that it's a principal axis, but the fact that these are coinciding tells you that this z-axis is also a principal axis. Okay. How do you know if an axis is a principal axis? How do you know if an axis is a principal axis? We're gonna do that later. It's called the Mohr circle, and that's gonna be in the next few sections. We're gonna use the Mohr circle to find out which axis is a principal axis. So that's what you can look forward to learning soon. Okay. So again, in the last class, we've done symmetric bending. Symmetric bending is when the moment is acting along a line of symmetry or a plane of symmetry. So what do you do when you have this unsymmetric bending? So this is not along any line of symmetry here. What do? You're going to break it into two components. Now we're on slide 8. Okay, so you're going to break this moment into two components where the axis is on a line of symmetry. Here, we say my because it's moving about the y-axis. Here it's mz because it's moving about the z-axis. Okay, so mz, it's moving about the z-axis, my, it's moving about the y-axis. Okay, mz equals m cosine theta. This is m, and this is theta. Mz is m cosine theta, so that's adjacent. This is the adjacent vector. Sine is opposite, so it's the opposite. It's the vertical vector here. So my is sine theta, mz is cosine theta. Mz is m cosine theta, my is m sine theta. Okay, notice also that this moment is going from left to right. So each of the two components is also going from left to right. Okay? So when you break it up into two components, make sure you have the right direction. Left to right, left to right, left to right. Okay. Next slide. Slide 9. So again, my is going about the y-axis. It's acting in the z-plane. Okay, it's acting in the z-plane. Mz is about the z-axis and it's acting along the y-plane. So here, the equations for stress, for mz, it's moving along the y-plane. That's why it's this y here. It's moving about the z-axis along the y-plane. My, it's moving about the y-axis, but it's moving along the z-plane. See that shaded plane right there? So that's why it's a z number right here. Okay. Also, be careful of the signs. So to the right of this T-beam, that's in what? Compression. To the left side of the T-beam, it's in tension. Okay, so for this my number right here, this term right here, the right side of the T-beam is compression, is negative. The left side is tension, is positive. So this sign right here depends on if it's more the right side or the left side of the T-beam. This moment's causing what? The top is in compression. So that's a negative. So the top area of the T-beam is in compression, negative, bottom is tension. So it's positive. So depending on if it's on the top or the bottom, that tells you what this term's going to be, either positive or negative. Top is compression, bottom is tension. So be careful of the signs. You need to manually put in the sign right there, depending on what part of the beam, what part of the cross section are you looking at. Okay, where is the neutral axis? How do we find where the neutral axis is? This is the equation for stress. This is from the moment about the z-axis. This is from the moment about the y-axis. You remember stress equals to my over I. Okay, so you have two terms because you broke it up into two components. We're going to make that stress term equal to 0. That's how we find the neutral axis. Okay, substitute. Okay, so we're in slide 10 now. So we're going to substitute moment about the z-axis equals to m cosine theta. Moment about the y-axis equals to m sine theta. Okay, so we're going to substitute that in. Okay. So stress equals to m cosine theta y over I z plus m sine theta z over IY equals to 0. We're gonna add the cosine over, so m sine theta z over IY equals to m cosine theta y over IZ. Okay, then we're gonna multiply the IZ over and divide the m cosine theta. So m sine theta z over m cosine theta IY equals to y. The moments cancel out. So IZ tan theta equals sine theta over cosine theta. So IZ tan theta over IY times z equals to y. Okay, so basically we have an equation of a line here. Okay, where y is the vertical axis, z is the horizontal axis, and this is the slope of the line. Again, a reminder, we are looking at how to find the neutral axis. So how do we find the neutral axis? So we just found the equation of a line for the neutral axis right here. Okay, so turn your turn to slide 11. Okay, so we found an equation for this line for the neutral axis right there. Okay, so the equation of the line for the neutral axis is y equals to the slope iz over iy tan theta times z. Okay, so the slope term equals to tan phi. Tan phi is from the horizontal axis to the neutral axis. So we have an equation of a line tan phi is opposite over adjacent, so opposite over adjacent equals rise over run, right? So tan phi equals the slope of the line, right? Slope is rise over run, that's opposite over adjacent. So tan phi equals the slope of the line. Okay? So that is how we can find, that's how we find phi from the horizontal to the neutral axis. That will equal to moment of inertia about the z-axis over moment of inertia about the y-axis times tan theta. Okay?